Gauss's law. Gauss's law is an alternative law to Coulombic inverse square law. See, Coulombic inverse square law can be used to calculate electric field or a force between the 2 point charges. But where Coulomb's law is failed to calculate electric field due to a object, there we can calculate electric field by using Gauss's law. Gauss law is an alternative law. Statement: the total flux through any closed surface in free space, this you have to understand, in free space is equal to 1 by epsilon naught times the charge enclosed by the surface. Okay, see this once again. The total flux through any closed surface in a free space is equal to 1 by epsilon naught times the charge enclosed by that surface. That means, for example, if we take, this is a Gaussian surface in which actually some charges are placed. Say Q1 is here and minus Q2, and here we have minus Q3, and we have here Q4. See, these are the 4 charges are lie inside the Gaussian surface. I will take few more charges outside. For example, say this is Q5, this is Q6. Like that, charges are there here, but I have selected a Gaussian surface of this one. Within the Gaussian surface, we have only 4 charges: Q1, Q2, Q3 and Q4. Q5 and Q6 are lies outside. According to this statement, the total flux through any closed surface, that closed surface is only called as Gaussian surface. So that flux we know it is denoted with phi, is equal to the total flux through any closed surface in free space. Free space means vacuum, or even you can consider air, that's it. You should not imagine a medium. That means comfortably I can write it is epsilon naught. Permittivity of free space or air or vacuum is equal to 1 by epsilon naught times the charge enclosed. This is also important. When you are calculating flux, you need to take the charge lies in the Gaussian surface enclosed by the surface we have to take it. So that means I will write a general expression for flux. Phi is equal to charge enclosed divided by epsilon naught. 1 by epsilon naught times charge enclosed is called flux through that Gaussian surface. Okay, if you want to apply the expression for this example, here flux phi is equal to, I need to take charges which are present inside the surface. That means I have to take Q1, Q2, Q3, Q4 only. Charge enclosed, total charge I have to write. Total charge means how to calculate, we know charge is additive, simply will add. When you are calculating the net charge, you need to take the sign of the charge because charge is a scalar quantity. When you are dealing with a scalar physical quantities, you need to take the sign of the charge. When you are dealing with the vector physical quantities, no need to take the sign of the charge because the direction will take care of that negative sign. This we have already covered in the previous classes. So now flux phi is equal to Q1 plus, but minus sign is there, so minus Q2 plus, but minus sign is there, plus into minus is minus Q3 plus Q4 divided by epsilon naught. This is the flux through the Gaussian surface. Okay, so we can even define this Gaussian law in a different way. That is, flux phi is equal to the circular integral of E bar dot ds bar also gives you flux, that is equal to charge enclosed divided by epsilon naught. Okay, I know charge enclosed, then I can calculate flux by using phi is equal to Q enclosed by epsilon naught directly. Okay, If you want to calculate electric field, then I can use this part of the expression, circular integral of E bar dot ds bar is equal to q enclosed by epsilon naught. Here ds is surface area, small surface area. D means small, delta means difference, ds means small surface area, delta s means difference in surface area. So when you want to calculate electric field by using Gauss's law, see, you have to understand this is important. Here charge here is enclosed, charge enclosed we have to take. But when you are calculating electric field at any point, for example, I want to calculate electric field at this particular point, I need to consider all the charges present inside as well as present outside, all I should take. This is very important. Okay, some important points related to Gaussian surface. The first one is, Gaussian surface is an imaginary surface enclosed by the charges. Here I have taken, say, this is a Q1, this is Q2, and somewhere here I have Q3. For example, this is one of the Gaussian surface. This surface is say S1. Okay, now I have another surface of any shape, doesn't matter. This is say S2. I have here one more surface, say S3. I have drawn there three Gaussian surfaces. What is the flux through surface 1? If I ask a question, flux through first surface is called say phi 1. See, this is the first surface. That means in first surface we have Q1 and Q3 only. So that's why charge enclosed is Q1 plus Q3 divided by epsilon naught. If I didn't say anything about the medium, we have to imagine that is a free space or air or vacuum. So flux through first surface is Q1 plus Q3 by epsilon naught, that's it. Flux through second surface. Second surface means this one, this surface. Here we have only Q2 and Q3 in it. So that's why that is Q2 plus Q3 divided by epsilon. See, here you have to even observe very carefully the sign of the charge. Because we are calculating flux. Flux is a scalar quantity, we know. Okay, so we must take sign of the charge, but here all three have taken positive, fortunately. Okay, so next flux through the third surface. Third surface means S3. S3 is containing all the three charges. So that's why I'll write it is Q1 plus Q2 plus Q3 divided by epsilon naught. Okay, so this is important. This is how you have to understand the first point. Second point, Gaussian surface is a vector. Here I will explain one simple example. For example, if you take a charge Q here, you draw a Gaussian surface as a sphere, for example. Sphere is a Gaussian surface now. See, if you want to calculate electric field at this particular point, then here I need to select a small surface area, ds bar. ds I have to take. See, this is ds bar. Surface area vector is, I have told already, it is always perpendicular to the surface and outwards. So that's why ds bar will be in this direction. Okay, so this is Gaussian surface only, we are selecting here small elemental portion. So that's why it is outwards. So it will have direction, so that's why it can be called as a vector. The last one, third one, flux through Gaussian surface is independent of its shape and size. So understand this, flux through Gaussian surface is independent of its shape and size. For example, we will see, I will take a charge Q1, Q for example. If I take a Gaussian surface as a sphere, flux will be phi is equal to Q by epsilon naught only. If I take Gaussian surface as some amoeba shape, then flux will be phi is equal to Q by epsilon naught only. Same quantity of charge lies inside any two Gaussian surfaces of any shape. Flux is same. Okay, second part is size. We will see that size part. For example, if you take a charge here, if I take a sphere of radius r, Gaussian surface of radius r, radius is r, flux is phi is equal to charge enclosed divided by epsilon naught. That's it. Where we have used in this expression dimensions of the Gaussian surface? No. If I draw another Gaussian surface of radius 2r, even though flux will be phi is equal to q by epsilon naught only by the definition. That means flux through any Gaussian surface is independent of both shape and also size.